this isn't exactly correct, but it more or less looks like a resistor capacitor circuit, more or less. And this is the capacitor. And as you know, what is the capacitor? It holds electric charge. As a resistor, okay, provides the resistance, and this charge is dissipated through this resistor. The capacitor charge is dissipated through this resistor, and there is a complex math that's involved in that. Well, if it's a very simple circuit like this, the math is relatively simple. If it becomes complex and complex and complex, so there you are. And what it does is it filters out voltages or current pulses, or you could say signals or whatever. So it can be connected to a source of current or voltage. Okay, so works with a voltage or a so current source, and this capacitor, it holds the charge, and it just lets a certain amount of charge through, which corresponds to the signal. So basically it is used to filter out the unwanted signals. Okay, I mean it is maybe when we are talking about electrical engineering or electrical sciences per se, this is used to give you a particular amount of charge. But in case of, say, electronics, including the electronics that we use in computers, we can say that this is used for cutting off certain levels of signals and uh, providing us with a certain amount of signal. uh, this is used for that. Okay, now the point is that this thing is very hard to fabricate on an IC chip in case of transistors. And transistors are obviously, they work with a very little amount of, and you have a very little amount of space. First of all, they are in the micrometer level. Okay, so you can imagine a micrometer level being so small, because uh, if this is 1 millimeter, let's say, okay, or let's say that if this much is 1 millimeter, then a micrometer is the one part of 1,000 parts of this. Okay, where my nail touches it, there, maybe this is a millimeter, about like that. And 1,000 parts, if you can imagine 1,000 parts of that, and then take one part, that is a micrometer. So transistor electronics actually work in the micrometer level, the microns. So the micrometer level, and it's very hard to actually fabricate something like this, and it becomes so much more expensive. And also, resistors, capacitors, nothing is not prone to uh, being busted out. Nothing is not prone to damages. Nothing is not prone to destruction. So if you want to build this kind of stuff, and as I say, that this is a very how should I say, a very simple thing. What you need in the digital circuits for filtering out the levels and only providing it with the edges may be much more complex than this. This is just a simple one. It may not be used at all. What will be used may be much more complex than this. And so obviously you cannot put this effectively in an IC. There are lots of different things to that. First of all, it'll increase the circuit complexity if you don't want. So if you increase the circuit complexity, that obviously means that you will decrease the longevity of and the maintainability of the circuit, which you don't want. And obviously maintaining a circuit is very hard if it's in the micron level. So what do we do is that if a circuit goes bust, then we obviously throw it out and put it back with the, I mean, put in its place, we put in another circuit. We don't actually, these days we don't actually, we normally don't mend the circuits at all, do we? We don't actually do that. For example, if you have a motherboard of a phone or a computer or anything, if something happens to the motherboard, there is no repairs as such. Rather, if you go to the high street shops, what they will ask you to do is just throw away the motherboard and get a new one. So it's hard to do that. So you can imagine from all of these that this is a simple one, but we need a more complex one than the most probably. And that kind of capacitor, you really cannot effectively build it because it's impractical. Even if you build it, you cannot maintain it. So what do you do in this case? You actually use something called coupled systems. For example, look at the direct coupled edge triggered D flip flop. Here the RC circuit is not there. The basically, so just one sec. So here basically what is happening is now I'm obviously going to upload this video, so I'll leave you guys to understand this by using a truth table, but just as a guide I'm telling you. So you can see that this is D coming in, all right, and it is a coupled system. Now what did we have for edge triggering? First of all, we obviously had, we could we could maintain, and I mean, what was wrong with the level triggering stuff? That we could, there was a very big window for which the data or the signal was visible, and we did not want that. If when we wanted the signal to be off after we have read it, that could not happen if the level stayed on. So that is why we had an edge, because an edge just passes off. So instead of having a level, we used to have an RC circuit which provided with an edge. So we provide with an edge, we read the circuit or we input and then we stop. That is why we were using edges rather than levels. So it's much easier to, obviously it's harder to design, but it's much easier to operate, and it's much more secure to operate these kind of devices which are edge triggered. How do you affect, okay? How do you affect an edge trigger with a level trigger then? How do you actually do that? Well, very simple. That when you couple this, okay, so there is 1 and a 0. So basically, rather 0 and a 1, it'll work alongside. If you just, as I say, that I'll leave you to first of all analyze this with the truth table. With a 0 and a 1, you will see that it will be on for some time and will off after that. Once again, when you provide a level, it will be on for some time and be off after that. Okay. This is why this has been coupled. So the direct couple means the coupling is not indirect but direct between two JK flip-flops, and this will it will act as if it was connected to a rising edge or a falling edge, as the case may be. Maybe this case is just a rising edge of a clock rather than the levels of a clock. Something very similar happens when you go for a master slave flip-flop also. Okay. Here is a master slave flip-flop. This is and out here, this is the reset, and this is a set gates. As you can see, some diagrams I've shown you, including the ones that I drew, were with AND gates and NOR gates, but this here they have used NAND gates and OR gates. Comes to the same thing. Okay, and also here they're inverting the signal, okay, to compensate for the NOR gates. So this tiny little dot here obviously means inverting it. And how does it work? Once again, this is to do away with the RC circuit. And look at what they're saying about the working principle. So while the clock is high, the master is active and the slave is inactive. When the clock is low, the master is inactive and the slave is active. So what does that do? When the clock is high, the master is active and it produces whatever you want to produce. So whatever QT was, if this was 0 and 0, it would hold. Otherwise, if it's set 1 and reset 0, then you have at QT plus 1, you have this thing, you have 1. And otherwise, if reset is 1 and set is 0, you at QT plus 1, you have 0. But then the slave to which the Q and the Q bar are located or attached, but that is inactive. Now when the clock falls, the slave becomes active and you can receive the values. So this is how it basically works. And you can see the feedbacks going into this. So how is it done? First of all, we create a JK flip-flop. Here we have two NAND gates and those signals are inverted into these two OR gates. Feedback of this goes into there and the feedback of this goes into there. Okay, and from the ultimate output, the Q output goes into this for reset. Okay, normally this is at the top, but here they have shown it as the one below. And then the Q bar feeds into the set gate here. The Q bar. Okay, and these two are connected to the clock. Now obviously there is a single clock, it works with a single clock. Now what will happen? Now this clock is here. When the clock goes low, what will happen? This clock signal, no. So this is now connected to this SR flip-flop or JK flip-flop if you like. And here also the construction is the same, except that this is just an SR flip-flop, so the outputs are not connected back to the input gates. Here the three input gates, these two input gates are three input gates. Alongside the clock, it has the data that you're feeding in as well as the outputs. And here in this case, only it has the clock and the data that you are feeding in, and the outputs are not connected. This is just a simple SR flip-flop, which is called the slave to the master flip-flop. Master flip-flop is obviously a JK flip-flop. Now when the clock is down, when the clock is up, this is down because of this inverter. And so this being down, nothing is available. Or shall we say it remains as this, or nothing is available, like that. If the clock is up, this one receives the 1 and it's working. Now when the clock goes down, this one is inverted as a 1 and fed into the SR flip-flop. Now whatever is coming in to SNR, so whatever is coming in to the SNR, if if it is 0 and 0, it will be as it was before. 1 and 0, set is 1, R is 0, this will receive 1. Set is 0, R is 1, this will receive. But when the clock is down, because it will be inverted to a 1, and now this will be 0, so this won't work. This will be 1, so this will be working. So what is the idea behind this? Idea is simple, very simple, that we are doing away with the rising and falling edges of the clock, so that we can avoid making an RC circuit to be built into the circuit like this.